Hello everyone, in this video we are going to be looking at sound waves. So first thing, let's look at audible sound waves. So audible sound waves are sound waves that human ears can hear, and normally the human ear can hear sounds that is originating from a frequency of 20 to 20,000 hertz. And then if we look at this, well, this 20 to 20,000 hertz on a scale, this is how much human can hear. 20 to 20,000. Elephant and moles, they can hear frequencies that is less than 20. And these frequencies that are less than 20 are called infrasonic. On the other hand, cats and dogs, they can hear a little bit above human, as well as dolphin and bat. Any frequency that longitudinal waves with a frequency that is above 20,000 hertz is called ultrasonic. So basically we are using humans as a divider. Anything that is below what human can hear are infrasonic. Anything above is ultrasonic. And let's look at this frequency idea in terms of a wave. That way we can visualize it better. So over here, they're plotting the same thing. And then here, this is the region for the humans. We can see that for the lower region, which is the infrasonic, the frequency is a lot less. So the frequency is how often a wave is occurring. So this is low frequency. This is high frequency. Okay. And then above 20,000 hertz is our ultrasonic. And you can see that the frequency is a lot higher, and that's why when we say we have medical ultrasound, that just means that that particular frequency is higher than what we can hear. It's in the region that is higher than what our human ear can normally hear. And when we are looking at how the audible sound waves are perceived by our ear, we can look at the fact that, well, the way how our brain receives sound is that we have an ear that consists of an external cone that directs the sound wave. So this is the cone region, okay, that is directing the sound waves to the eardrum. And then as it enters the eardrum, the vibration of the sound is going to move the ear bones and vibrate the oval windows. And so over here, it's going to vibrate this region. We would just say it that way. And then where the sound is being detected. And later on, this sound that is being detected is being passed through the auditory nerve that is sending the signal to our brain. The way how our brain interprets a frequency is that it interprets it as a pitch. So when we are looking at a lower frequency and a higher frequency, that corresponds to lower pitch and higher pitch to our brain. So for a viola, it is a lower pitch, which is a lower frequency. On the other hand, we have a violin, which is higher pitch and then corresponding to a higher frequency. When we are looking at how sound can travel, a medium is required. So when the transmission of a sound wave requires a solid, liquid, or gas to carry the disturbance. And the sound does not travel when there's nothing to carry it. So we can imagine that, well, we need little particles to carry our sound waves. So when we're in vacuum, we're in outer space, there is no sound because there's nothing to carry the sound. Therefore, we cannot hear anything when we are in outer space. But then when we are on Earth, we can see that, well, we can hear sound through air vibration, through water vibration, so we can hear things when we are standing in air as well as when we are diving. And the nature of the medium depends on how well and how rapidly the substance can carry sound wave. And this depends on the inertia of the molecule as well as the strength of the interaction. And in general, sound is moving through solids more rapidly than through gas. And so the rate of sound is solid is faster than liquid than gas. So looking at the velocity of sound in air, one thing we note is that, well, light travels faster than sound wave. So let's compare the differences between sound wave and light wave to start with. So based on this graph, we can see that light waves, they do not need a material medium to carry it. So they can travel through vacuum. That's why when we are in outer space, we can still see things. We can still see light. On the other hand, sound waves, it does require a medium. That's why when we are in outer space, we cannot hear anything. And sound waves are longitudinal, and then light waves are transverse. And sound wave has a lower speed than light waves. And this is why when there is a lightning strike, we see the lightning before we hear the sound. Same idea as when we look at fireworks, we see the firework before we can hear the sound of the firework. And this is just because light waves, they're traveling faster than sound waves. So when we are looking at the velocity of sound waves in air, it is highly dependent on the temperature. So the gas molecules in warmer air, they have a greater kinetic energy than those of cooler air. And this results in the speed of sound being faster in warm air than in cooler air. And in general, the speed of sound increases in 0.6 increments for each Celsius degree increase for a temperature that is above 0 degrees Celsius. And when we're in dry air, the speed of sound is 331 meters per second. So, based on these two descriptions, we can write an equation. The velocity that is at the temperature that we're looking at is equal to the velocity at dry air, so the velocity of sound at 0 degrees Celsius, plus, remember, it's 0.6 for each Celsius degree, so it is 0.600 meters per second per each Celsius degree. And this multiplied by the temperature that we are looking at. So here, okay, I'm going to rewrite this because that was ugly. So remember, the velocity at the time we're looking at is equal to the initial velocity plus 0.600 meters per second per 1 Celsius increase times the temperature that we're looking at. And in this case, Vt is the velocity at the temperature that we're looking at, and the units is in meters per second. The V0 is the velocity at 0 degrees Celsius, which is equal to 331 meters per second. And this is also equal to 1086 feet per second. And then the big T is the temperature that we're looking at in degrees Celsius. So when in this particular version of the equation, this is in meters per second, so the V0 should be this one. We can also write the same equation in terms of feet. So it is Vt equals to V naught, which is the same thing. And instead of 0.6 meters per second, we're going to use 2.00 feet per second over 1 degree Celsius multiplied by T. And in this case, as we can see, we are feet per second, so the V naught will be 1087 instead of 331. And this is just something that we'll need to remember when we are using the equation. It's just that with different units, we're going to need to plug in different things. And hopefully that we can realize that we have the wrong number in when we are working with the units. So here is an example. So over here, it is asking us what is the velocity of sound in meters per second at room temperature. So when it is 20 degrees Celsius. So the first thing we know is that, well, we are looking for velocity. So V is what we're looking for. We're looking for velocity at a certain temperature. And that temperature we're looking at is 20 degrees Celsius. So that is going to be, our temperature is 20.0 degrees Celsius. These are the things that we know. So because we are finding a velocity at a certain temperature, we know that the equation we will be using is the velocity at certain temperature is equal to the V initial plus 0.600 meters per second over 1 degree Celsius multiplied by the temperature. Now VT is already on its own, so we don't need to rearrange the equation. We can just start by plugging numbers in. So first thing is we know that V0 is a given number, is 331 meters per second. And we are using 331 because over here we are looking for meters per second. We are also looking for meters per second here. So it's going to be 331 meters per second plus 0.600 meters per second over 1 degree Celsius multiplied by the temperature is 20.0 degrees Celsius. Remember the orders of operation, we need to do the multiplication first. So the next thing we're going to keep 331 meters per second. Multiplying these two numbers, we know that well. We are going to again do the numbers first. So 0.6 divided by 1 multiplied by 20. And that is going to give us 12.0. For the unit part, it is going to be meters per second divided by Celsius multiplied by Celsius. And as we can notice that the Celsius can be crossed out, so what is left is meters per second. Now they are the same unit, both are of them of meter per second, so we can add them up, and that is 343 meters per second, which makes sense because the units make sense because velocity is distance over time, and this is meters over seconds. For this question, I hope that you can take some time to pause the video and then try it yourself and come back when you are ready. So looking at this question, the first thing we know is that, well, it says that the air temperature is 86.0 degrees Fahrenheit. What is the velocity of sound in feet per second? So first thing we know is the temperature is 86.0 Fahrenheit. So the temperature is 86.0 Fahrenheit. We're looking for the velocity at this temperature, so that means that we're looking for VT. Okay, so we know that eventually in order to find the velocity at that temperature, we're going to need to use the equation where it says VT equals to V0 plus 0.600, and because in this case we're looking for feet per second, so we'll actually be using the other equation, which is 2.00 feet per second divided by degrees Celsius multiplied by temperature. However, as you can see that this requires the temperature to be in degrees Celsius to cancel out. So the first thing we need to do is actually convert the 86.0 Fahrenheit to Celsius. We have to do this before we plug it in just because this equation has to be in degrees Celsius to cancel out, or else we're going to have units that cannot cancel out at the end of the day. So to convert Fahrenheit to Celsius, we know that we can use the equation where Tc, which is the temperature in Celsius, is equal to the temperature in Fahrenheit minus 32 times 5/9. So this is the equation to go from Fahrenheit to Celsius. We have Fahrenheit, so we're going to replace this number with what we have. That is 86.0 minus 32 multiplied by 5/9. We're going to do the thing in the parentheses first. So 86 minus 32, that is going to be 54. Multiplied by 5/9, that will give us 30 degrees Celsius. Now with this 30 degrees Celsius, then we can apply this equation. So now we found that this is equal to 30.0 degrees Celsius. So that's what we just did. And then the second step, we can now plug it into the equation that we were hoping to plug in. So the key thing here is literally remembering that we need to be in Celsius. Also, if we are looking for feet per second, then we are going to need to use a different equation than if we are using meters per second. So the equation, I just erased it, but I'm going to write down the exact same thing. VT equals to V0 plus 2.0 feet per second divided by 1 Celsius multiplied by the time. So here we're going to plug in our numbers. So V0, when we are looking at it in units of feet, it is going to be 1087 feet per second. So again, because here is feet, so we need to do feet all the way. Feet here, and then feet here. So that way later on our units will cancel out. And if at the end of the day when you're trying to cancel out the units don't cancel out, you know that there is a conversion that you're missing. So over here we have 1087 feet per second plus it is 2.0 feet per second divided by 1 degree Celsius multiplied by temperature, which is 30.0 degrees Celsius. We're going to need to do the multiplication first. So again, we are going to start by writing down the number part. So the number part is 2 divided by 1 times 30. And that is going to give us 60. And the units, you can see that the degree Celsius and the degree Celsius cancel out. That's why we had to convert it. And what is left is feet per second. And after adding them up, it is going to be 1147 feet per second. And this is the unit that the question is looking for. And we see there's no excess units going on. So that means that we did it right. So the next thing we're going to talk about is the movement of the sound wave. So when we're looking at sound waves, you probably already see this diagram before where we have the source of the sound wave, and then the way how we represent it is their concentric spheres. So we can imagine that if we are doing it from a distance, then it's going to be a line. So we do have a linear wavefront when we are far, far away. So what this lines means is that these lines are the condensations. So remember that when we are looking at longitudinal waves, which remember sound are longitudinal waves, we have regions where we have more dense air particles, and then they just look like this as longitudinal waves are generated. And then in the middle, we have lighter density ones. And what these lines are depicting is the condensations or compressions that are over here. And remember that in the middle, the one that is less dense, they are called rarefaction. So sometimes you can see that they are linear wavefronts, and then sometimes you can see them represented as concentric circles, but remember that the lines are the condensations. So when we are looking at the movement of sound wave, one of the things that we can imagine is that sound wave can travel through different medium. And the boundary, the division between the two different physical conditions is called a boundary. So it can be between two different materials or between the same material at two different conditions. So it can be, let's say we are passing the sound from air to water or water to an ice cube. That's just me unable to come up with a better example. So let's talk about refraction. So here that refraction is a bending of the wavefront in boundaries, and this changes the direction of travel of the wavefront. And the sound, like we discussed previously, it travels faster in higher and warmer air than it will in lower and cooler air. The result of this is that, well, over here on the left, you can see that there is a person calling his dog. And if we have cool air on top and warm air at the bottom, because it travels faster in warmer air, so this voice is going to bend up. Because you can imagine this side is running faster than this side, so eventually it's going to bend the direction. Same idea, if we have cool air on the bottom and warm air on the top, this is going to go faster compared to this one. So at the end of the day, the sound is going to bend down. And that is changing the direction, it's bending the wave. And one thing that we can see is that over here, so we have day and night scenarios. So during the day, our ground is going to heat up faster, so it's going to be warmer on the floor, and the air is going to be cooler. Therefore, the sound wave is going to be faster in the warmer air than the cooler air, so it's going to bend upwards. Compared to at night, the ground cools faster because it's solid, and then the air cools slower. So in this case, the sound is going to bend down because on the top it is faster and on the bottom it is slower. And this is why the music you play at night are generally louder, just because it is bending towards the ground instead of going in air. Another type of movement that the air can have is reflection. So then when we're looking at reflection, it is undergoing a change in direction. So previously we're just bending. Now we are changing a direction. And then this can bounce directly back or it can deflect off an angle. So when we say directly back is we can imagine that we have a speaker over here, and then it's going to have an original sound wave. After it hits an object or a wall, this sound wave is going to reflect directly back. So this is one of the possibilities. Another possibility is we have a speaker and then we are talking to the wall from an angle. Okay, that is again me unable to come up with a better example. And then it is going to reflect into a different angle. This is also reflection. So this involves a change in direction. And this depends on the nature of the boundary. The wave can be a little bit absorbed, so we can have a lot of wave going in, some of them being absorbed by the medium, some of them bouncing out. So it can be absorbed, it can be transmitted, it can be reflected, or a combination of all of them. So just to wrap up what we were talking about, where the sound can undergo reflection and refraction. When it is a reflection, then we are literally changing the direction. When it is a refraction, then it is just bending between the two different media. And this, we can see this in terms of when we are looking at acoustics. So over here, when you are taking an ultrasound, this is the incoming wave. Some of the wave is going to be refracted as it hit your muscle. Some of the wave is going to be reflected directly up towards the soft tissue that you have. So it's not either or. Both of them can happen at the same time with different proportions. So please don't feel like it is either refraction or reflection. It can be both at the same time. When we have a mixing in the reflected sound plus the original one, we have something that is called a reverberation. So this adds volumes to the tone. And you can imagine that we have let's say an instructor speaking in the classroom, right? Other than the original one that is going directly into the student's ear, the sound can bounce off the wall and reflected multiple ways, and that will increase the tone and the volume of a tone. So that would just make the volume of our sound louder. And if the reflected sound arrives after 0.1 seconds, that we can distinguish between the original and the reflected one, which is like you yelling into a tunnel, and then you can hear the differences between your original one plus the echo plus the reflected sound that's come back, then that is called an echo. So it is like, well, you see the dry sound, so we hear it once, and then it is going to echo that we can basically hear it twice and our ear can distinguish it. It's an echo. So because we know that the sound wave can echo, and we do know the velocity of sound underwater, we can use it to determine the depth of the water and to locate underwater objects using a sonar device. So a sonar is an abbreviation of the sound navigation ranging. And it generates underwater ultrasonic pulse, hits the floor or the object, and then echoes back. And if we measure the time, then we can find the distance travel, right? Because we know the velocity. So remember, we know velocity equals to distance divided by time. So we know the velocity of sound in air because this is going to be constant, and we can find the different velocity at different temperatures if we measure the temperature. So we do know the velocity. If we have a sound beam traveling and then wait for it to come back, then we have the time. So with that, we can know the total of distance for the sound travel. So for this particular submarine, the total distance travel is down and then up. So then the distance, like the depth of the water, is just the distance that we found divided by 2. The reason why we have to divide it by 2 is because it's not only down, but also coming back up, and both of them should be the same distance. So from that, let's look at this example together. So it says that the human ear can distinguish a reflected sound pulse from the original sound pulse if 0.10 seconds or more elapse between the two sounds. What is the minimum distance to a reflection surface from which we can hear an echo if the speed of sound is 343 meters per second? From here, the first thing we know is that, well, the time needs to be 0.10 seconds or more. So we know by here, the time needs to be at least 0.10 seconds, minimum. The second thing we know is that, well, it is asking us for the minimum distance. So we're looking for distance. And then it tells us that the speed of sound is 343 meters per second. So the velocity is 343 meters per second. With this, well, we know that by definition, speed equals to distance over time. So if we are trying to solve for distance, wanting to get that by itself, we're going to multiply both sides by t. And with that, we can see these two t can cancel out. So it's t times v equals to d. That will be the equation that we use after we convert it. So d equals to v times t. And now that we can plug in our numbers, so velocity is 343 meters per second multiplied by time, 0.10 seconds. That is 34 meters. However, remember that we are looking at a reflected sound. So the total distance that this sound travel is going forward, hit something, and then coming back. So the distance is two-way. So in order to find the distance for one way, we have to divide this number by 2. So then we will do 34 meters divided by 2. That is 17 meters one way. And that will be our answer. So it is basically 17 meters between this. It is 34 because we go and then we come back. Idea over here is another example. I hope that you can take a moment to pause the video, try it yourself, and then come back when you're ready. Welcome back. So in this question, it says that an echo is heard exactly 1.00 seconds after a sound when the speed of sound is 1147 feet per second. How many feet away is the reflecting surface? The first thing we know is that, well, we have 1.00 seconds, so that is our time is equal to 1.00 seconds. And then it says that the speed of sound is 1147 feet per second. So we know that the speed is 1147 feet per second. It is asking us how many feet away. So that means that we know we are looking for distance. So from here, again, we are going to use the equation for the velocity. So we are going to first start by finding the distance traveled. So find d travel. We can do this by knowing that v equals to velocity equals to distance divided by time. Because we're looking for d, so we're going to multiply both sides by t, so that way we can get d by itself. So it's going to be d equals to t times v. And then we're going to plug in the numbers, so it's 1.00 seconds multiplied by 1147 feet per second. From here, the first thing, again, remember we do the numbers first. So that is going to be 1147. Then looking at the units, it's seconds times feet over seconds. So seconds will cancel out. What is left is feet. So this is the total distance traveled. But we're looking for how much distance is one way. So we're looking for one-way distance. So remember, when we're looking at this, the distance we look for is round trip. Now the question is only for asking for a single trip. So we have to divide our round trip distance by 2, and that is 573.5 feet. And that will be our answer. So looking at this, well, the sound can travel, but remember that the sound, there are usually more than 2 waves in the same situation. So when we have 2 traveling waves, they meeting each other, they can interfere with each other and basically create disturbance to each other. And there are 2 different kinds. There are constructive and destructive disturbance that we're going to be discussing. So first thing, let's look at constructive interference. So constructive interference is saying that if our wave crest and then the wave troughs are at the same place. So we have wave number 1 and wave number 2. Their crest and troughs are in the same place. Then we call them in phase. The result of this is that the amplitude of their combined wave is going to be adding up the 2 small ones. So this is called a constructive interference, where the new disturbance, it has a crest and a trough that has a greater displacement than its original one. So we can see that originally this is wave number 1, and then this is wave number 2, and after then we add it up, so you can see that we have a bigger amplitude. And remember, amplitude is basically the height of the wave. So A and B are this tall, and then after we add A and B, it's this tall. And that is our amplitude. And we can also think about it on a string. So we have A and B, the 2 waves meet. When they meet, they are in phase. So the resulting wave is taller. And then after they hit each other, they separate again. But at this moment, they're undergoing constructive interference. The second type of interference we're going to talk about is destructive interference. So this is the case where the 2 waves have the troughs and crest perfectly avoiding each other. So this is wave number 1, and this is wave number 2. You can see that when wave number 1 is high, so at its crest, wave number 2 is at its trough. So when the 2 waves meet, the resulting one is going to have a smaller amplitude than the one that it originally had. So this is the one after they meet. And we can see that, well, this is the amplitude of A, this is the amplitude of B, but then after those 2 meet, it is smaller. And we call them out of phase. And when this happens, well, we can imagine that the crest is going to cancel out the trough. So basically, it is a destructive interference. And looking at the example down here, we have one going A meeting B, but when they met, because they cancel out, what they met is a flat line, and then they separate out. So here are just summarizing what we just talked about. We have the constructive interference, where we can see that our heights of wave 1 and wave 2 are the same. Destructive interference, when one is high, the other one is low. When one is high, the other one is low. So they cancel out to be a flat line. And we can imagine that if we have 2 sound waves, so remember that we can also express the sound wave in sphericals. And then the lines are the wavefronts. So the lines are the point when it is high. So this is the first wave, and then this is the second wave. So we can imagine that when the lines meet, so when we have an intersection between the lines, then these are the constructive interference, because their crests are meeting each other. So remember, each line is the height of the crest. And then if in the middle, where their crest and their trough meets, so like along this line, when there's only crest and not another crest, then they have destructive interference patterns. And another interference can be beats. So beats are regularly spaced increased and decreased sounds. And you can see that we are basically having alternating constructive and destructive interference. So here we have wave number 1 and frequency number 1, and we have frequency number 2. At this point, we have constructive interference because their crests are meeting each other. This point, we also have constructive interference. However, over here, there is a destructive interference, meaning that they cancel out. And the constructive interference increases the amplitude. So that's why we have a bigger condensation for the sound wave. So remember, sound waves are longitudinal waves. So we have a higher density of air molecules when it is constructive interference. And then the destructive interference results in a rarefaction. Rarefaction, remember, is the portion when it's less dense, and condensation when it is more dense. So that's why we can hear the beat, because all of a sudden you have constructive interference that is increasing the volume. So we can calculate the frequency of the resulting beat. So we have the frequency for F1 and F2, and we can calculate the frequency of the resulting one, which is this one over here. This is the resulting beat using the following equation. So we know that the frequency of the beat is going to equal to F2 minus F1. It is literally looking at the differences in frequency for the two interfering waves. With that idea in mind, thank you for watching this video, and I'll see you in another one.